Hello there, and welcome to day 19 of the Advent of Code challenge. Wow, this was another hard one. Um, as before, I started recording and I realized I wasn't going to be able to do it in any reasonable amount of time. And so I stopped my recording. It took me until the early hours of the morning to finish it, but I did it, and I'm going to give a little overview of my solution. Don't forget that if you're looking for hints or solutions, you can always check out the Advent of Code subreddit. There is there are plenty of people contributing to that subreddit, and so you can find some help there. I did have a glance through the subreddit this morning, and I noticed I couldn't see anyone that did it the way I did it, and so that's kind of interesting. So I'll give a little overview of my solution. Again, I'll assume you've read the problem description. It's not. It is another long one. There's plenty of examples in there. But I think where we'll start is just with this. I'm going to skip all the parsing and all that stuff because that's not very interesting. So I'm just going to give an example that with the example data, which is the example data is the stuff in the problem description. Actual data is my actual data. Yeah, so you'll see, for example, here, I believe, this is a set, so the ordering is different. But you'll see, yeah, here we go. So this is scanner zeros data right here. I think it's probably better to start with the concept of how I am approaching this. What I'm doing is I'm taking a set of points. So let's pretend my fingertips are the points. I'm taking a second set of points, and I am going to rotate it and try different rotations and see if I find any rotation where the points and these points align. Right, and if they align, I'm going to add these rotated points and translated points into this map of the ocean, I guess, based on the problem description. So now I have a bigger set of points to match against. I'll take another scan result. I'm going to rotate that until I find a rotation that matches. Going to match it to the existing set of points, and then add it to that, and then keep going until I've mapped every set of points like this, right, into the ocean, and then I'll have my global set of points. Now, of course, that makes sense, but you have a lot. The question is, how do you actually rotate your points? How do you actually map them to it? That is the crux of this problem. And so for rotations, I just went straight to my graphics, 3D graphics coursework material. I just Googled for translation matrices, rotation matrices. I found this website. It's the top Google result or something like that. And the problem description does mention that there are 24 possible orientations, and they are all listed here, all 24 of them. And if you don't know how to read matrices, I think this isn't really the place to explain it. But what you can do is you can translate these matrices into different rotations, mappings. You know what, let's just really briefly explain how to do matrices. Matrix multiplication, if I have a matrix 1, 0, let's not do the first one. Let's do the second one, 0, 0, 0, 0, minus 1, and what's the last one? 0, 1, 0. If I multiply that by my vector, which in this case is x, y, z, imagine these brackets are giant brackets around the whole thing. Then I'm going to get the point x here, the point minus z here, and the point y here. Now I hope that makes sense. That's just the basic matrix multiplication with vectors. But that's how you can read these rotation matrices. And so what I did was I just wrote this out on paper and then just typed it all up. Every single possible rotation. I used an ID, 0 to 23, to represent them. I could represent them as matrices in here, but then that's just an extra step that I didn't have to do. So I kind of simplified it into, you give it a vector, you give it a number from 0 to 23, and it will spit out all the different rotations that are possible for this vector as defined by the problem. So that was the first step. That's that's all the rotations done. I can take any point and churn out all 24 possible rotations of that point. And so we can actually kind of see that in action, I think. Let's just take, for example, this set of points. I'm just going to replace some test data here. Let's do this. Oops. We'll do this. So that should be the 5th block. Where is it? Cool. And what we can say is, let's say for every point in that scan, we will print out the point.rotate. So let's try and get it to the second one, which I think was rotation 2. No, it wasn't rotation 2. Maybe it was rotation 6. I remember some of these numbers, but not really. We can work this out, like 5, 6, 4. This is minus x minus z minus y. Minus, okay, so it's rotation 5. Okay. So here we go. So you see that we took in this set of points as the original, but here is a rotation that maps it to this set of points here. And so it's important that we're able to just rotate all these points. I think part of the trouble or the difficulty with this problem is that if you're not used to manipulating points in 3D space, reasoning about how do you do rotations, how do you do translations, that is probably the hard bit. If you are, I was lucky enough that I had done a little bit of 3D programming before, so I have vague ideas of how these concepts work, but definitely not an expert in them in any way. But yeah, that was the first step, being able to freely rotate all these sets of points in a nice and easy way. Now, I think I should just mention really briefly here that my data types that I'm using. So scan result is just a map of vector3 to bool, and I'm using this as a set. Now in Go, a proper set uses an empty struct like this because then it actually uses 0 space. Here I need to store an extra bool, which is an extra either a byte or an int or 4 bytes. I'm not sure what the actual low-level representation is. So this is less space efficient, but I've always found that using empty structs to represent sets leads to very clumsy looking code. It looks very cluttered. And so I don't like to do that. For something like this, I'm just going to use a bool. It makes my code easy to read. Yeah, so I stick with it. I stick with that for that representation for sets and Go. And then I just have a vector3 type, which is just x, y, z. And then it has some basic helper functions, which I've defined further down in my code. It's exactly what you would expect them to do. So we have the ability to rotate our points. And so how do we map points to each other? So the first thing I do is I do what the problem suggests, and I use the first scan result as my basis, right? It's the coordinate system that I'm using for everything else. I'm trying to map everything else to the coordinate system of scan 0. And so just I called it ocean because that's what the problem called it. What I'm going to do is I'm going to add every point after mapping it to relative to scanner 0. to a new set of points, which I call ocean, which is going to hold all the unique points in the entire result. And so we start with every point in scanner 0 is by definition going to be correct because they're going to be already be relative to itself. And so all those go into the ocean right here. I need to track where all the scanners are. That's actually for part 2, so we'll ignore that for now. So what do I do? Well, for every remaining scan, and so I dropped the first one because we've already mapped them all. For every remaining scan until they're all mapped, what we're going to do is, we'll skip down to here, take every possible rotation of that scan. So it is actually brute forcing it. Take every possible rotation of that scan. We rotate to the first orientation. Now, does this map to the points in the ocean? How do we do that? What I've seen some people do is they map, they try to map the relative location, they map all the distances between all the points within a certain set, and then they try to look for overlap that way. I did it a different way. I took every point in the set and I calculated the offset, the translation vector from that point to every existing point in the ocean. Okay? And then I take the next point and I do the same thing. And then I store all those in a map. I store the point as the key, and then the number of times that specific translation vector occurs between these 2 points sets as the value in my map. And so that's what this is, right? We have all the offsets for every point in the ocean, for every point in my scan. I calculate the offset between the two according to the current rotation that I'm testing. And whatever that offset is, I increment the count in my offsets array map. Now, if this rotation has points that fits with the point in the ocean, certain translation vectors are going to occur multiple times because the points map, right? And it doesn't matter, I don't have to know which point to map it to because I'm just trying all of them. But there will be certain translation vectors that occur multiple times. And according to the problem definition, at least 12 of those beacons will map between scans. And so I just say, once I've gotten all the offsets, I just check, is there any specific offset, any specific translation vector that occurs at least 12 times? If there is, then that translation vector and the current rotation, whatever it is, that is the correct set of values to map this scan to my reference frame, my reference coordinate system. This took a little bit of trial and error, but it turns out that the scanner position is going to just be the inverse of that translation vector. So that's what I do. And then all I do is I take the points in my scan, I rotate every point, rotate it with the current rotation. I translate it. This add is a translate. It's a vector addition. Translate it into that coordinate system, and then I add that point to the ocean. And then that's done. So then that specific scan. All those points are added into the final result. And then because this scan is done, then I'm just deleting the scan. This is just basic Go. And then I keep going. And then I keep going until we see here every scan. I just loop over the scan once I've mapped, because not all of them will be able to map to 0 to the first scan either, right? So I might loop to the nth one. That one matches. So I add all those to it. I remove it from the array. And then I just keep going over all the scans until I've mapped all of them. Yeah, and so that's pretty much all there is to this. You can see here that I'm getting the results that it says in the description. The first one that's mappable is scanner 1. That's mappable relative to 0. And I have that translation vector. This 12 is the number of matching points, and the 6 is the specific rotation. It's the ID of the rotation. So that doesn't actually mean anything because there is no specific ordering to these matrices. It's just whatever order I ended up with. Yeah, so this is the translation vector for scanner 1. So, and this is the rotation. So I rotate all the points to that. I translate them all into the thing. I add it to it. And then we find the next one, which in this case, let's see, minus 20. So scanner 4 is the next one that is mappable. So then we do that, we rotate that, we map all the points to it with a bigger array, a bigger set of points and so on. And then yeah, at the end, because this is a set, it already by definition contains the unique points in the ocean. So I just print out the length of it, and that's part 1, so 79. And then the second part is actually quite straightforward. It's just a max over all the points, right? You just loop over the point, every pair of points, and then calculate the distance between them, which is just implementing the algorithm as they defined it, Manhattan distance. It's just got some typecasting in there because Go is pedantic about that sort of thing. And then you just do a max, and you print out the max. I did get caught out by part 2 because originally I didn't add in the 0, 0, 0 vector for the first set of points that we mapped in, right? Scanner 0 is by definition at 0, 0, 0 in our reference coordinate system. And it turns out that if you don't have it, the example works fine. Oops. The example works fine. And you still get the right answer, 3621 here. But with your actual data, I don't know if this is true for everyone, but at least for my input, without that 0, 0, 0, the answer is wrong because there's a point that is further away from 0, 0, 0 than between itself. And so I add it back in and I get a slightly bigger number at the end, which was my actual answer. So I did get caught out by that. But yeah, so that's a very brief overview of how I did it. I guess I'll chuck this code up on a gist so you can take a look at it if you want to and try to understand it a bit better. I hope that was somewhat useful. It's a slightly different way to calculate it, but if you want, once you're a bit more familiar with how to manipulate and reason about points in a 3D space, how you can manipulate them, then the whole problem becomes a little bit simpler. I think wrapping my head around rotations and translations. If you ever did 3D programming, you'll know that the order of rotations matter, for example. If you rotate by matrix A and then rotate by matrix B, it's not the same as rotating by matrix B first and then matrix A. And you can get caught up by that in this. Rotating and then translating, again, it's different from translating and rotating. So these operations aren't commutative. And yeah, so it's just it's just knowledge like that. I think it's good to have bits and pieces of how that is supposed to work or how they work floating around your head. And then when you need to, you can pull it back up. You can pull up some tutorials, some references like this, and then you can understand it and you can do something with it. So this was a really brief overview of my solution. Thanks for watching this video. And I'm hoping for easier problems, but it looks like it's only going to get harder from here. So best of luck for the rest of the challenges through this Advent period.